Cambridge, and since 2022, he's now a faculty at the University of Mississippi, which is also in Oxford.
Great. Okay. Yeah. Thanks for the invitation, and thanks everyone for coming along. So I'm going to talk about graviton scattering and bootstrap bounds, and this is work with Hinterbeckler and also Delma Mazach and Shredik Pao, based more or less on these bunch of papers. So feel free to interrupt me and ask questions if I explain something badly or you want me to say more details about anything. So here's a bit of an outline. I'll give some overview. Then I'll talk about Kaluza-Klein reductions in graviton scattering. Then I'll talk about bootstrap bounds for Einstein manifolds. And at this time, I'll talk about bootstrap bounds for hyperbolic manifolds. So these first two sections, this is work done with Hinterbeckler, and the last section is work either on my own or with Mazach and Pao. So let's start with this overview. So the motivation for this, at least for this audience, is going to be from thinking about scattering amplitudes of massive high spin particles. So if you have a theory which has some massive spinning particles in it, and you calculate some scattering amplitudes of those particles, generically these amplitudes will grow at large energies, like some power of the center of mass energy E. So the amplitude goes like center of mass energy to some power, and this bad high energy behavior comes from the fact that the massive spinning modes have longitudinal modes. So for example, you have massive Yang-Mills theory, the W and Z bosons in the spin model, and you scatter them without any other states, and this amplitude goes like the square of the center of mass energy. So this exponent n is equal to 2. If you increase the spin a little bit and consider massive spin 3/2 particles.
This is not Higgs.
Not Higgs, yeah.
Then this problem goes away, right?
Exactly. Yeah. Right. Yeah, so this is without the Higgs, you have this bad growth, which is one reason why they had to discover something like the Higgs to fix this problem. Yeah. So for spin 3/2 is even worse. If you couple massive spin 3/2 to gravity and nothing else, you get e to the 4 for the 2 to 2 tree level amplitude. And for spin 2, massive spin 2 is even worse. You have n equals 6 for the massive spin 2 particle in this DIGT massive gravity. Now we can do
for regular gravity, it's E10, isn't it?
for massless gravity, it's E squared.
Or no, without this DIGT, and just
Just like a generic massive gravity,
yeah,
it'd be like e to the 10.
E10, right?
Yeah. Right. But then
So this is a very special theory to get E6.
exactly. Yeah, you have to appropriately tune the interactions. And it's the same tuning that makes the theory goes free that improves the high energy behavior. Those two things are linked. And this is the best that you can do just for a single massive spin 2 particle. So you want to be able to do better than this because this bad high energy behavior is tied to a violation of perturbative unitarity at some low strong coupling scale. So for the massive Yang-Mills case, we all know the famous resolution, which is to add an extra scalar particle, the Higgs boson, and then that makes this bounded at high energies, giving you a renormalizable theory. For spin 3/2, one way to improve the high energy behavior from e to the 4 to e squared is to integrate in a scalar particle and a pseudoscalar particle. This was nicely explained in Wenshi and Tony's recent paper. And that gives you broken n equals 1 supergravity. For massive spin 2 particles, there's no way to integrate in just a finite number of lower spin particles to improve the high energy behavior. But as I'll talk about on the next slide, one solution is to include an infinite number of extra particles.
The gravitational cases, these are presumably then suppressed by powers of that Planck, right?
Yeah, so
So the bad behavior only happens.
so in the massive spin case, it's the cube root of m squared in Planck. So there's some scale which is parametrically lower.
It's good. Because there's M Planck and there's the middle M. So
Yeah.
It's kind of it's like a geometric mean, but not a geometric mean. Some scaling.
How do massive revolves in your language?
So they have an infinite number of massive high spins in addition to the collisional states. Yeah, that's like a high spin completion if you're thinking about a larger than QCD. Yeah. Or in glue balls, their mass is actually at the QCD scale, so they're like right at the cutoff anyway. You know something has to happen at that scale. Yeah, good questions. So one solution in the case of massive spin 2 particles is to think about Kaluza-Klein theories. So you start with a theory of massless spin 2 particles, namely general relativity, in high dimensions. And if you Kaluza-Klein reduce it, you get a equivalent description in terms of a lower dimensional theory, which has an infinite number of massive Kaluza-Klein excitations. And these Kaluza-Klein excitations are massive spin 2 particles. And since this Kaluza-Klein theory is just secretly a rewriting of the high dimensional theory, the amplitudes of the lower dimensional massive spin 2 states should inherit the good high energy behavior of the massless high dimensional graviton. So there must be some conspiracy between all the Kaluza-Klein states, their masses and their couplings, which gives these massive spin 2 states improved high energy behavior. And the questions that this talk is going to answer are firstly, how can we see this from the lower dimensional point of view? That you get this improved high energy behavior? And then what else does this imply for the lower dimensional physics? So let me give you a basic overview of the calculation. So you start with high dimensional general relativity on a product background spacetime, which is the product of some lower dimensional Minkowski space and some compact internal Riemannian manifold. You then integrate out to compact dimensions using harmonic analysis, basically, and you end up with a lower dimensional theory, which has these infinite towers of particles. And the masses and interactions of these particles are determined by the geometry and topology of the internal manifold. So the squared masses are related to eigenvalues lambda of various Laplacian operators, and the cubic couplings, which are denoted by C, are writable in terms of integrals of products of the eigenfunctions over the internal manifold. Once I have this lower dimensional theory, I can just go ahead and calculate, for example, the 2 to 2 scattering amplitude of the massive spin 2 Kaluza-Klein excitations of the graviton, just by combining all the diamond vertices. I take this amplitude and I can expand it in a high energy expansion. And it starts with this generic massive spin 2 behavior, which is the 8 to the 10, like we just talked about. And it has these subletting terms going all the way down to e squared. And these coefficients alpha are just some combinations of the coupling constants and masses and the other kinematic variables. The perturbative unitarity of GR tells you that this amplitude is secretly just high dimensional graviton scattering, which goes like e squared. So this should also go like e squared, which means that these first 4 terms should cancel. So namely these coefficients should vanish. Yeah.
So when you do the dimensional reduction, do you assume there's a massless graviton? And what would happen if there was, would it dimensionally reduce without a massless? I mean, I guess some of these coefficients then would not be good.
So you have to have the massless graviton,
You do.
I would say. Yeah. It's sort of unavoidable.
Because you could compactify and not have massless graviton, right? Then
If you somehow took this theory and you just like crossed out the massless graviton,
yeah,
it would ruin this.
I mean, there's ways to do it. But that would just give you a theory of massive gravity again, and I think all these coefficients would be non-zero again, that's what would happen. So it sounds like it's important that you need the massless 4D gravity.
Yeah, at least with my setup, it's going to be compulsory.
Yeah.
Yeah. The massless graviton, it just corresponds to the constant mode on the internal space. I can always have that. And you see that in more detail soon. You could, I mean, you could start with massive gravity and then dimensionally reduce it.
No,
and then you
I'm
could
saying just start with massless,
Yeah.
but then,
Yeah, the way I do it, we'll always have to have a massless graviton.
because you can do that with the gauge field, you see, you can compactify a gauge field, you don't necessarily have to have a massless vector. You could project out the massless vector and have a massive scalar, so probably the same thing could be true. Probably here, if you actually project out the massless 4D mode, you'll just have a theory of a massive vector and a massive scalar. That's pretty good.
Okay, yeah, maybe ask me again once I've shown more details and you can tell me what you have in mind. Yeah. These vanishing conditions, they'll give us some sum rules. And these sum rules give you some constraints on the masses and the coupling. So then the question is, how can we extract useful information from these sum rules? And to do that, we can follow a bootstrap procedure, which is analogous to the conformal bootstrap. And then lastly, this is the hyperbolic manifold part of this talk. You can generalize these constraints and find much more powerful bootstrap bounds for this more restrictive class of manifolds called hyperbolic manifolds. Okay, any other questions about this outline before I get into some details? Yeah.
The number 4 there, that's what you know has to happen, and that's what you're trying to see does happen.
Yeah, physically, you think it should happen, and we'll check that it does in fact happen, and it's like a theorem. Okay. Yeah. But we learned something interesting by seeing how exactly it happens.
Using the cyclotron and the thermals, that is similar.
Yeah, they do something similar.
So can you comment on the relationship between your study and I think you are using Bootstrap method. That's something more general, or you
I would say
reproduce their results.
this first part is the same. They are trying to like check that it goes like E squared, but they're looking at I think it's a random syndrome model, so it's like having one extra dimension, where it's like a Z2 orbifold. I'm going to have arbitrary extra dimensions, which are compact manifold. So it's like, this is like having more dimensions for the internal space. Yeah. And then they kind of diverge after that, what we do. But yeah, there's some similarities and overlap. Okay, so let me talk about Kaluza-Klein reductions in graviton scattering. So we start with the d-dimensional Einstein-Hilbert Lagrangian, big D dimensions. And we consider a background spacetime, which is a little d-dimensional Minkowski space, crossed with some closed manifold M. Closed just means compact without boundary. And this has, let's call it big N dimensions and volume B. And I'm going to assume it's connected and orientable. So then I can write the line element as the sum of two parts, corresponding to the low dimensional Minkowski space and the internal manifold. So I'm going to take the coordinates on the internal manifold to be called Y, and the spacetime or the space indices to be N.
So your geometry necessarily factorize with it.
Yeah, I'm assuming it's like a product manifold. You could consider a more general thing like warped products, but I'm gonna stick with this.
Yeah. Is that your hyperbolic manifold stuff at the end?
No, that's
Oh, that's hyperbolic on the internal.
yeah, it's hyperbolic on the internal.
But in general, non-factorizable geometry.
You could do, yeah, you could like redo this whole thing, starting with a more general, but it's going to be more complicated. Yeah. Because it really, yeah, it helps me like disentangle the constraints on the internal space. So since I've taken the low dimensional spacetime to be flat, the vacuum Einstein equations tell me that the internal space also has to be Ricci flat, meaning it's Ricci tensor manifolds. So for this calculation, the internal space furthermore has to be Ricci flat. So now we can expand the full metric perturbatively around this background that I just discussed. So I write the full metric as the background plus a perturbation, which is the high dimensional graviton. And I've included some normalization to make the graviton canonically normalized. You plug this in to your high dimensional Einstein-Hilbert action and expand, and you give it quadratic order, the usual kinetic term for a massless graviton. And then you have the cubic interactions, which is suppressed by the high dimensional Planck mass and the quartic interactions and so on. Also, you have the high dimensional diffeomorphism invariance, which acts at leading order as these linearized diffeomorphisms on the high dimensional graviton. So now I need a bit of an aside to define some Laplacians and their eigenmodes. So I'm first going to define the scalar eigenfunctions, which I'll denote by phi subscript I. So these are eigenfunctions of the scalar Laplacian, which I define with the minus sign. So the eigenvalues lambda I are some non-negative numbers. I also need the eigenvectors of the one-form Hodge Laplacian. So this is the natural Laplacian on vectors. So I'll denote these eigenvectors by y m. Remember, this was the vector index, and I is just a label. And furthermore, these are going to be transverse or divergenceless. So they satisfy an eigenvalue equation for this vector Hodge Laplacian, where the eigenvalues I denote by lambda I with a superscript 1. And these are non-negative. And then lastly, I need the eigentensors of the so-called Lichnerowicz Laplacian, which is the natural Laplacian operator on rank 2 tensors on an Einstein manifold. And these are also going to be symmetric, transverse, and traceless. So I index them with an index I, and they satisfy this eigenvalue equation. The details of this Lichnerowicz Laplacian won't be important. And I denote the eigenvalues by lambda I superscript 2. So I have these 3 different Laplacians on scalars, vectors, or rank 2 tensors.
So you do have massless scalars as well.
There will end up being massless scalars.
Yeah.
Yeah. There's always one, which is like the shape modulus. You can have others. Sorry, the volume modulus you always have, and you can have shape moduli as well.
And presumably that's going to be important for the unitarization.
Yeah, they will play a role. Yeah. So these eigenvalues are all discrete and unbounded from above and bounded from below. And the corresponding eigenmodes will form bases of the respective function spaces. So this just follows from standard results of spectral theory and compact faults. Okay. So now we're going to try and decompose our high dimensional graviton. So I start with the high dimensional graviton, and I can break it up into its different components. So for example, this h mu nu component, this looks like a tensor from the point of view of the lower dimensional spacetime, and it looks like a scalar from the point of view of the internal space. So I can decompose its dependence on the internal coordinates using an eigenfunction decomposition of the scalar eigenfunctions on the internal space, using the fact that the scalar eigenfunctions form a basis for smooth functions on the internal space. So I end up with a decomposition which has this following form. So these phi i's, remember, are the scalar eigenfunctions of the Laplacian. And the coefficients in this expansion are tensor functions depending on the lower dimensional coordinates. But these are going to end up corresponding to the massive spin 2 modes, or the massive spin 2 mode in the lower dimensional theory. Similarly, for these off-diagonal components, they look like vectors from the point of view of the lower dimensional spacetime or the internal manifold. So I can first decompose the internal vectors using a Hodge decomposition to write them as a transverse piece plus a longitudinal piece. And And then I can decompose each of those pieces using a spectral decomposition in terms of the transverse vector eigenmodes and the scalar eigenmodes for the longitudinal piece.
And they're always massive. That's the implication of the way you've written it there. They're always massive.
They're not always going to be massive.
So the longitude won't be there necessarily. Zero.
I'm going to end up fixing this to be 0 using a gauge fixing. Yeah. But these coefficients here are going to be the vectors in the lower dimensional theory. And they can be massless if there's a killing vector on the internal space. And then lastly, the HMN components. These are tensors from the point of view of the internal manifold. So I can first do like a tensor Hodge decomposition where I break the tensor up into longitudinal and trace pieces. And then I can decompose each of those pieces. And this transverse traceless part I can decompose further using a sum over the symmetric transverse tensors of the numeric part. Each of these comes with a coefficient, a scale function from a lower dimension. Okay, so that's the sort of generic spectral plus Hodge decomposition. This is just the general analog of doing a Fourier decomposition. You just had like an extra circular dimension. You would just Fourier decompose the fields on the extra dimension. This is the generalization of that to an arbitrary compact internal space. Now, because I had this high dimensional different Boltzmann invariance, that turns out to give me a gauge freedom, which I can use to fix the longitudinal modes of vanish. So I'm going to do that from now on. And then there'll be some residual gauge symmetry, which will show up as the low dimensional diffs of the graviton, and possibly the Yang-Mills gauge symmetry if I have massless vectors as well. So plug this position into your high dimensional Lagrangian, and once all the dust settles, you can read off what the spectrum of that low dimensional theory is. And this is what it looks like. So the vertical axis here is the squared mass, showing the spin 0 modes, the spin 1 and the spin 2 modes. So you have two towers of spin 0 modes, tower of spin 1 modes, and a tower of spin 2 modes. And for example, the masses of this tower of spin 2 modes are determined by the eigenvalues of the scalar Laplacian on the internal manifold. The masses of the spin 1 modes are determined by the eigenvalues of the one-form Hodge Laplacian on the internal manifold. And they might possibly be 0 if they're killing vectors. So the internal manifold has some non-trivial isometries. And then you have one tower of scalar modes corresponding to the scalar eigenvalues. This came from the trace piece and the decomposition of the metric. And you also have another tower coming from the transverse traceless part of the composition, whose masses are determined by the spin 2 eigenmodes of the internal space. Okay. And you can have some massless scalar modes, which is moduli. You always have this one, which is the volume modulus. You can have additional ones, which are called shape moduli, depending on if your Einstein manifold admits deformations which preserve the volume. And a priori, these eigenvalues are not necessarily positive. You could have tachyonic modes, but it turns out that for all known Ritchie flat manifolds, you don't have tachyonic modes. In particular, if your Ritchie flat manifold has what's called special holonomy, it's a theorem that the spin 2 eigenvalue modes are non-negative. Okay, so this is your spectrum.
So the absence of the longitudinal modes is only the case for the ground state particles, or when you said you removed all the longitudinal modes?
So they are like the would-be longitudinal modes of these massive states.
There would be.
Getting the unitary gauges like they get heated to become massive.
Right. Okay, so on the previous slide, when you said there are no longitudinal modes.
That would be if we're explicitly like expanding the massive modes as like transverse plus longitudinal with separate fields.
Oh,
But I'm
okay.
fixing that gauge symmetry, so it's really just a massive mode
Okay.
without any
Oh.
subgroup symmetry.
If you remove the scalar modes from those states.
So these
Remove
are
additional scalar modes.
proper like massive modes, so they have longitudinal pieces, but I haven't
Well,
like separated them out.
Not the spin zero, but spin zero has no longitude.
Sorry, I was
Pointing to them.
Yeah, but
pointing
can't
at the wrong
you,
one. This one, this one.
yeah, but can't you think of the spin one at the massless level? Can't you think of the spin one and the spin zero as they would have been eaten if they become massive? Could you think of it that way? or
Yeah,
not?
so if before I crossed out those longitudinal modes, I could have drawn some extra towers. And then I could say I'm doing like a Higgs mechanism where I'm going to eat them to form massive towers.
No, I meant just, I think Keith's question was at the massless level.
Um,
So at the massless level, you can never think of the spin one or the spin zero as ever getting eaten at the massless level.
yeah, these are,
Yeah, okay.
there would be longitudinal modes of the killing vectors aren't there because it's,
So
Yeah.
the next X up, the next blue X up.
Yeah.
Right.
Yeah.
That one has a longitudinal mode.
yeah, this
Okay.
has 3 degrees of freedom and
Okay.
in 40. Yeah.
And if you wanted to write it without it, you would have another column of scalars or?
Yeah, if I wanted to like separate out that and then give it as like a
Okay,
cycle.
I just want to understand what you meant by that.
No, that's a good
one.
one. Yeah. It's like a Stuckelberg symmetry.
So another question though is, so for spin two,
Yeah.
the tower there, so there are 5 degrees of freedom, and so that's like having another vector, if you want, and another scalar.
Yeah,
So that X is all 5 of them?
that's all 5 of them.
Okay.
Yeah.
And in addition to the 5, I see, okay, in addition to the 5, then you're getting which are like the off diagonal ones, which are the spin,
Which are
spin one. and then-
separate full massive. Yeah.
Right, okay, good. I got it.
Yeah, good.
So on the previous slides about the scalar modes, there are two contributors. One is a trace term, the other is this
Yeah,
eigenvalue.
there's one hidden in there and then there's this one.
Yeah, how are those two contributions reflected in the next slide? Which one is trace term? Which one is this the eigen?
So this is from the trace.
This whole tower is the trace.
Yeah. And the other one is from coefficients of the transverse traces.
Are there any reason you label the tower black?
Just because it's the same as the spin 2 tower.
In terms of spectrum.
It's the same spectrum.
Its origin seems like separate.
Um,
From the decomposition earlier, it seemed to be separate entities.
yeah, well here, so this is like the internal manifold times the scalar, and then just doing a spectral decomposition on that scalar, and so it looks the same as this. That's with the scalar here instead of a tensor. But it's the same eigenfunctions, so the spectrum is the same.
What was sigma then, without the tilde?
That was the one hidden in this trace.
Oh, that's in the
I didn't
trace.
show you what it was, but
But then there's another tower from the HIs, no?
yeah, this is the Coda one. That's the green tower.
Okay,
And inside the trace here is the
no, but from the first line,
up here.
yeah,
These are the lower dimensional fields. This is the internal. Depends on the internal
oh,
fields, why.
okay.
I integrate over all the y dimensions. So I'm just left with this.
But it's still another tower, but that tower is not on your next slide, is that?
It's not another tower.
It's not another tower.
No. It's just the
It's just the metric in 4D. It's just eventually it's just an expansion of the metric in 4D.
so this is some function of x and y.
Right, I'm thinking of it as the metric a priori.
So this, I mean,
That's the fluctuation.
That's gonna be the fluctuation.
H mu naught.
Okay,
this comes from like the constant eigenfunction on over square root of volume.
right, that's the massless part. But what about the first term there?
Yeah, so these are my massive vectors. Sorry, my massive spin particles. Once I integrate out the y.
Okay, those are the black ones on the right.
These are the black ones
okay.
on the right.
Okay, good, all right, sorry.
Yeah. Yeah.
Okay. Yeah, you even have it labeled, all right, sorry.
Okay.
But what sets the scale for the KK spectrum? Is it just one mass parameter? Is it like I mean, how many parameters in your internal, you just have one parameter or many parameters, or obviously? it
Yeah,
doesn't
it's like the
matter.
overall volume. So if I rescale like the volume, then we'll rescale all eigenvalues.
But typically these volumes have more than one mass parameter that can set scale spectrum. Is that true?
I mean, I would say that overall volume is like the one thing that I want to fix. And then once I fix that, the spectrum is just like whatever works out.
You're referring to shape or deformations.
Yeah, depends on the details.
Because I was
of the
just
geometry.
interested in knowing, what, is there an upper bound on the lowest massive state?
Right, at fixed volume, that would be a well-defined question. Yeah. If I'm allowed to rescale the volume, then I can sort of make it as large as I want.
Yeah, but I want to fix the volume and see how far I could push that lowest lying state.
Yeah, that's the kind of thing I'm going to talk about
Oh,
in the bootstrap part.
oh,
Yeah, exactly that kind of question.
Oh, are you going to actually eventually bound that? Is that what you're going to do?
Let's say the manifolds.
I see.
So that was the spectrum, which is just the free part of the theory. But to compute amplitudes, I need the interactions. So for example, I can get the cubic interactions by just looking at the cubic part of the high diagonal Einstein-Hilbert Lagrangian, plugging in my decomposition, and I end up with some terms which have the following form. So there's an infinite number of these massive spin 2 modes, and they a priori can all interact with each other. And their interactions are determined by these CIJKs, which are these coupling constants, which are determined by the geometry as the integral of the product of the 3 corresponding eigenfunctions. So really it's CIJK times the square root of the volume. This sets this scale of the interaction in units of the low dimensional banknotes. Similarly, I can look at the cubic interactions between, say, 2 massive spin 2 modes and one of these towers of scalars, and then that being proportional to this CIJK superscript 2, which is just an overlap of 2 scalar eigenfunctions and the tensor eigenmode. And there's also a 4-point contact piece, which is proportional to this what I've called CIJKL, which is just the integral of the product of 4 eigenmodes. So once I have all these interactions, I can find the time invertity and calculate the scattering amplitude. So, for example, if I consider the scattering of 2 massive spin 2 modes into 2 other massive spin 2 modes, I have schematically some diagrams which look like this. There are infinite sums over these exchanged massive spin 2 states. Here's the graviton, here's the infinite tower of massive vectors, the infinite towers of scalars, and then the contact piece. I can calculate this, go away and expand it at high energies, and check whether or not these first 4 terms vanish, like we said that they should based on the overview I gave at the beginning. So if you do this and then see what we get, if I restrict for simplicity to the case of identical particle scattering, so I'm going to take all these external massive spin 2 modes to be the same state, HI, then the first condition I get from the vanishing of the e to the 10 part gives me the following summary. It says that some combination of the quarter coupling and an infinite sum of squares of cubic couplings plus 1 over the volume should equal 0.
So these C's are completely computable once you specify the internal manifold?
Yeah,
So-
in principle.
Well, suppose you took it to be a sphere,
Yeah, then it's just like Clebsch-Gordon coefficients.
okay? And then you can check,
Yeah.
you can just plug them in and see that this is true or not.
At the next subleading order, the e to the 8 part, I get this summary. So it involves the infinite sum of the squares of the cubic couplings with some three factors depending on the eigen values. And then so on at the next subleading order, e to the 6, start getting contributions from the scalars, which show up in these cubic couplings between two massive spin 2 modes and the scalars. And similarly at the e to the 4th order. So these are some conditions which should be true if the high energy growth goes like e squared, which we think it should. But we can just check directly that these sum rules are indeed true. So let me now tell you how to do that. So you just have to use the nice properties of these eigenfunctions. So for example, I know that the eigenfunctions form a basis of smooth functions on the manifold, the internal manifold. If I take the product of any two eigenfunctions, this is again a smooth function, so I can expand it as a sum of eigenfunctions. I can expand it as follows, and the coefficients in this expansion are precisely theseCijks, these overlaps of three functions. And I'm going to use this weight contraction notation to mean that I take two eigenfunctions and I expand them using an appropriate eigenfunction expansion. And so now I can derive our first sum rule. So I start with the quartic overlap, then fill the product of eigenfunctions. And I just expand the two pairs using this eigenfunction expansion. And then I get an integral of the product of these infinite sums. And I can use the orthonormality of the eigenfunctions to do the integral. I'm just left with this infinite sum over squares of the cubic couplings. And this is precisely what the first sum rule was telling us. The fact that this combination should be 0 just follows from this very simple argument. And it turns out all of these other sum rules can be derived by similar arguments. You just have to consider more complicated integrands where you have derivatives acting on the eigenfunctions. So for the next one, I just start with this integrand here, and I evaluate it in two different ways by expanding different pairs of eigenfunctions. And when I equate those decompositions, I get the sum rules that I needed for the amplitude to grow like e squared. So this is where they come from. And this argument doesn't restrict us to Ricci flat manifolds. It works for any Einstein manifold. So you can derive more general sum rules, which are true for all Einstein manifolds. And this is basically the answer to my first question. How does this e squared behavior come about? It comes about because of these sum rules, which in the end you can derive using this pretty simple kind of argument.
But does this exhaust all the possible sum rules that you could obtain using this method? Like I could add more derivatives.
Yeah.
Other sum rules, are they all just irrelevant or what's it called?
So all of these phi's are the same. And I want to be on a general Einstein manifold. I think this is a complete list.
So there is some completeness about this.
Yeah. The amplitude argument sort of gave me everything. Once I restrict to manifolds with constant sectional curvature, then I can have arbitrarily many derivatives and get an infinite number of sum rules. So that's going to be the hyperbolic manifolds. Sorry.
And you need, what do those infinite number of sum rules correspond to? You don't have infinite number of coefficients.
Right. I don't know a physics interpretation or a physics calculation that spits those out. Just applied by this answer, it's like just carry this further, no longer thinking about amplitudes anymore, and just see where it goes. But yeah, this is the answer that you get from the amplitude calculation. And I think that's probably the all that you can get.
So you got those from studying the identical particle scatterings, right? So you are sure there's studying, other particle scattering don't give you additional.
Oh no, you do get different ones if you have unequal particles. Yeah, you get like a dozen more. So
yeah, so there are additional relations between those coupling coefficients.
Yeah,
Yeah,
when you have unequal particles, yeah.
The question two is, from the derivation, I saw where the v minus one terms come from, but
Yes.
from my scattering point of view, to unitarize them, why do I see a v minus one term?
So that corresponds to the massless scalar coming from the voiding,
So
the-
mass is multiple.
or the massless gravitons. Yeah.
I give you.
Because the normalized massless eigenfunction is just 1/√v.
But sorry, but shouldn't this also generalize if you don't, so you assume the closed manifold, no boundary. What
Yeah.
happens if you have a boundary? If you have boundaries?
So when I derive these as a lot like integrating by parts, in principle, if you had a boundary, you'd have to worry about those boundary terms.
But it should work.
Integrate by parts, you get some identities, yeah. I think like in the Chivicula where
Exactly, because I'm remembering
have this.
what Chavukula did, he had boundaries and he was getting non-trivial sum rules as well, but he had
Yeah.
boundaries, so this should work even if you have boundaries.
Yeah, in principle, you could, you consider like a compact but not closed manifold.
But can you prove that there's also the mass loads?
I mean, I think there has to be because it's just well, if you're compact, then you can always have the constant eigenfunction is always normalizable. If you're non-compact, then you don't have like the identity, so then you wouldn't get a massless limit. But for compact manifolds, I think you always have to have.
Yeah, but then that would, see, but that would then contradict with the DRGT, which is E6, right? So, because I was thinking that,
Yeah.
could you reproduce your result with no massless modes? But that would contradict what DRGT did. It would be something different from DRGT.
If I took this and I just eliminated the massless. Well,
I guess, let me ask my question another way. Can you compactify and get DRGT? The answer is
not using a standard compactification.
right.
They can do like this funny discretized.
Yeah, I meant a standard.
No, using a standard one,
Impossible.
I mean, you have to have, you basically have the whole tower or you don't have any massive modes. It's, I'll show that from the sum rules as well soon. Yeah, that was like part of the motivation of this was thinking about could you sort of engineer a large gap so you can integrate out all the heavier modes and end up with like something that's here to T, but it'll turn out that's not possible. Okay, so let me move to this part of the talk, which is bounce manifolds. So let me quickly tell you or remind you what an Einstein manifold is. It's a manifold that satisfies the vacuum Einstein equations, so that if you tensor is a constant multiple of the metric. I'm going to assume that the manifolds closed connected are interval or a quotient of such a manifold. So some examples would be stairs and the projective spaces with their economical metrics. Things like Clactori or Calabi-Yau manifolds, or more exotic things like N7 manifolds or G2 manifolds. Okay, now we have these sum rules, which contain infinite sums over squares of these cubic couplings. Not a priori obvious how you could extract anything in the information from such sum rules, because they involve an infinite number of unknown quantities. There's a similar problem with the CFTs. So here's a little table which summarizes this analogy. For the case of manifolds, we have these eigenmodes and the spectral data consisting of the eigenvalues of the Laplace operators and the integrals of products of eigenfunctions. In the CFT, you have conformal primary operators and the conformal data consisting of the scaling dimensions and OPE coefficients of the operators. On the manifolds, we have an eigenfunction expansion, which is analogous to the OPE operator product expansion in a CFT. And we have these sum rules for the manifolds, which are similar to the crossing equations for a CFT. So there's a well-known solution to this problem in the case of conformal field theories, which goes by the name of conformal bootstrap. And the most famous example of this is this precise determination of this scaling exponents in the three-dimensional Ising model. So So these groups using these theoretical tools and lots of numerics are able to show that the 3D Ising model has to live in this small island in this space of parameters, which correspond to the scaling dimensions of the lightest two scalar operators in the theory. And this suggests then a solution to a problem, which would be like a geometric or a spectral bootstrap. So the idea is you have to first postulate some candidate spectral data. You then try to find a contradiction with the sum rules using some sort of optimization, like definite programming. And then if you find a contradiction, you can conclude that the candidate data cannot possibly come from a closed manifold. And so in this way, you can get constraints on this spectral data. So roughly, the crossing equations take the following form, where I have some infinite sum of vectors with coefficients which are non-negative. The sum rules tell you that this linear combination of these vectors must vanish. And depending on the vectors you have, that may or may not be possible. So for example, if all of these vectors fall on one side of a plane, then there's no positive linear combination of them that can ever equal 0. So you postulate some spectrum that determines these vectors, and then you try and see if there exists a plane such that they all fall to one side of that plane, thus showing that they could never satisfy the sum rules. You can automate this search using this nice program called SDPB, which was written by Davidson and Staffen for the conformal bootstrap. Okay, that was a bit fast. Does anyone want to ask anything about this before I show some plots? Okay, so here's the first kind of bootstrap bound for Einstein manifolds that we can get. So here I'm assuming that the Ritchie scalar is non-negative, and I'm showing here an upper bound shown by these colored lines for the different dimensions of the internal space. And the y-axis is the ratio of the first two non-zero eigenvalues of the scalar Laplacian. And the horizontal axis is the first spin 2 eigenvalue divided by the first spin 0 eigenvalue. So in terms of the spectrum of particles, this is like the ratio of the squared masses of the first two lightest massive spin 2 modes. In terms of the lightest scalar in the power coming from the transverse traces tensor modes. So in particular, if you have a stable compactification, which means this ratio is non-negative, then you can see that this ratio is bounded above by 4. What that means is that the massive spin 2 states can't have masses that differ by more than a factor of 2. You have the first lightest massive spin 2 state, the next one has to be a mass equal to twice the mass of the first one. That's what this is telling you. And you can saturate that bound for particular flat tori, showing that it's an optimal bound as well. And here I've shown some of the projective spaces as well.
Can you do that for the next levels as well?
So yeah, this factor of 4 is true for, turns out to be true for any two consecutive ones.
And it's always the same manifold that saturates this out, or not?
So if you want to do like lambda 3 over lambda 2, you can get a stronger bound, which is less than 4. And I think the expectation is the tori should always be the ones that saturate. There's a particular type of tori where you make one direction really big, the low-lying eigenvalues are the same as the other.
I'd be surprised that you have such a nice and smooth curve, or maybe there's a kink. It's a numerical scanning program of those towers of parameters, right? You're trying to find the boundaries of those relations.
I think because I only have 3 sum rules, it's maybe not that surprising. Once you get like, even with 3 sum rules, though, you do get things that are exotic. But I'm not sure, yeah. Sometimes you can explain things like this by finding examples that live right in this region. But I don't know any for this plot. So another thing you can bound is the size of these cubic couplings. If I assume again that the Ritchie scalar is non-negative and that the lightest spin to eigenvalue is non-negative, so it's a stable compactification. Then you can find an upper bound on this combination, the square root of the volume times the magnitude of the lightest massive spin 2 mode's interaction with itself, C111. And so depending on the dimension, the strength of this interaction has to be less than or equal to these numbers shown here with these two elements. So if you were to discover the lightest massive Kaluza-Klein mode in your accelerator and you could somehow measure its interaction with itself, this would tell you how many extra dimensions you would have to have in order to reach a certain value.
Right, n counts the number of extra dimensions or the total dimension.
This is the extra dimensions. Yeah.
What's the result for one? N equals 1.
If it's just a circle, I think it's 0.
Well, all different the choices. It's all 0. No self.
For the lightest one, yeah, this is just like integral of cosine cube. I think they started diverging after that. Yeah, I think so for this one. Yeah, I'm not sure why.
So string theory is would be like 6.
Yeah, 6 or 7. I think it's right. Yeah. Okay. So that was for Einstein manifolds. Let me say a little bit about the hyperbolic manifold story. So now I'm sort of forgetting about the whole scattering amplitude motivation, and I'm just sort of doing a mathematical physics problem. Yeah.
When you said that there are no interactions for just one extra direction, this is because you're starting in higher dimensions with a phase 3. Is that right?
It's GR.
Just GR. Okay.
Yeah.
So massive GR.
It's GR.
Not okay.
There are interactions between like different ones. Like the,
Okay, I see. But there's no. I see what you're saying.
it's just a stop
Thank you,
interaction.
thank you. I understand. But if you had, so this is just pure GR in higher dimensions, so just Ritchie scalar, right? Because in principle, you can't take that too seriously. There's in principle higher derivative corrections, and does that change the story?
That won't change the story, assuming like this background solution is the same. Yeah, it's
It won't change.
I guess assuming, because I assumed like the spectrum all came from the quadratic part of the action. And these higher derivative modes just like modify the interactions at higher orders.
Exactly. So the statement that there are no interactions sounds like it would be sensitive to whether you say it's just Einstein-Hilbert or Einstein-Hilbert plus corrections.
Say again, yeah.
So I understand that the spectrum will just come from the lowest derivative.
Yeah.
But to get whether or not you get self interactions, that seems like it would be sensitive to more. No, or maybe not. I haven't thought about it.
So yeah, if I add like out of the 4,
Yeah, part of the 4, for example.
then I'll have like additional contact terms that will have some like coefficient
Yeah.
alpha. Maybe I should put alpha, but then I'll get a bunch of extra interactions in the low dimensional theory.
Yes.
Between my KK modes.
Yes. Could you get some interactions even in the case where there's one extra dimension from such things?
I can have like Gauss banana 5D.
Yeah.
That's kind of thing.
Yeah, exactly. For example, yeah.
So that will give me some extra interactions, and I could like redo this whole thing.
Yeah.
And I guess the high energy scaling would be worse in that case. Depending on the interactions I add. It might go like e to the 4 or something. But presumably I'd get some sum rules, which would tell me how that energy goes down to e to the 4 in the low dimensional theory. But I don't think you'll get any new sum rules compared to what I've done here. Yeah.
Thanks.
Also, you had a small d for your effective space-time dimension, so this is like d equals 4. Small d equals 4, or it
It
doesn't.
doesn't matter what the lower dimension would
It
be.
doesn't matter.
Yeah.
Oh,
This is now, this is just a statement about the internal space, but
oh,
yeah, I've sort of decoupled all of that lower dimension, the d-dimensional stuff now. The sum rules only depend on the internal manifold.
so would it make sense for d equals 2? For d equals 3?
Yeah, you could do it, but I mean, a lot of the modes would be like topological.
So there is no propagating graviton.
Yeah, so I wouldn't be able to do the scattering amplitude calculation, but these bound on the couplings from the extra dimensions would still have to be true.
But when you say you have these bounds,
Yeah.
that was some bootstrap procedure, numerical procedure. How do you know that applying it more rigorously that these bounds could be lower? What was in the bootstrap that you concluded that this was it from bootstrap?
This was that in the sense of like no more sum rules,
Or the bound is stable there, it's not going to be lowered, or
I think for this plot, these are actually computable as exact numbers. I just did the numerical approximation.
so there's actually an exact calculation that you can do to get these.
For this one, yeah, because there are only a handful of sum rules. When you have like 100 sum rules, then you sort of have to use numerics. But you can even then make it rigorous, like in rational arithmetic, by taking your like numerical output, rationalizing it, and then like explicitly checking that it satisfies the conditions that you've imposed. So yeah, I'll mention some hyperbolic bounds, which are actually rigorous based on this reasoning. Okay, I guess I'm out of time, so let me do like a 2-minute summary. So for hyperbolic manifolds, this is like a further restriction where you have constant negative sectional curvature. So this includes things like Riemann surfaces of genus 2 or more, or you can get hyperbolic manifolds in 3 dimensions by doing what's called hyperbolic Dehn surgery on link complements. So for example, there's this like 3-component link on these mugs. This is the hyperbolic link, so I can do Dehn surgery on it to get a bunch of hyperbolic manifolds. And for hyperbolic manifolds, it turns out you can have an infinite number of sum rules, so you can get even stronger bounds. So for example, here's like the allowed values of lambda1 and lambda2 for genus 2 surfaces. So this line here is the bootstrap bound. The other lines are various other bounds that mathematicians have found. And this black line is some example genus 2 surfaces, which you can see fall quite close to the bound. You can also do a more complicated bootstrap setup where you have external holomorphic conforms, and that lets you find bounds on the first eigenvalue. So maybe this is the most impressive result. You can show that the first eigenvalue, the scalar Laplacian on a genus 2 surface, must be less than or equal to 3.8388977. And you can compare this to this famous genus 2 surface called the Boulder surface, whose first eigenvalue is 3.8388873. You can see that the bootstrap result is really close to the example manifold, and it's a similar thing in genus 3. And then you can play around with hyperbolic 3 manifolds as well. And then a year of my life was making this plot, which I'll skip over. And it also turns out that these hyperbolic sum rules, in a sense, are applicable to CFTs themselves. So the 2D Ising model satisfies the same sum rules as a hyperbolic 3 manifold. And so this is some interesting future direction that we're thinking about. Okay, so I'm going to conclude there. I found some bounds on spectral data of Einstein manifolds by Graviton scattering calculation. And then I said that maybe you can get more interesting bounds for hyperbolic manifolds. This might teach you something about CFTs. Thank you for listening, and I'm happy to take further questions. If you have any.
You get that high energy behavior down to E squared, but isn't E squared still problematic?
In the sense that it becomes sort of a couple of Planck scale, yeah.
Oh, okay, so it is then just at the Planck scale. Oh,
Wow.
because then you lose this extra. Oh, okay, good. Okay.
Yeah,
But then you have the non-renormalization of gravity and all that comes.
yeah. It's
Okay.
actually, it's a little bit worse because it's a high dimensional Planck scale, which is lower than the lower dimensional Planck
Yeah.
scale. Yeah.
So, like, in principle, if you do detect this gravitons scattering collider,
Yeah.
then you're like infer the coupling constants, and then you can conclude something about the manifold. If it's like it comes from extra dimensions, then I check with your table and I can like say like how many dimensions do I have, or whether it's hyperbolic or not.
Yeah,
In
in principle,
principle.
that's the like, I'm sure like anyone who's actually like a phenomenologist would tell me that doesn't work, but.
Yeah, but like, okay, well,
Yeah,
my question is like, so since for Ising, it's like comparable to hyperbolic manifolds. So what can you conclude about Ising from that observation?
oh yeah, so the hope would be that you could, so using the like Lorentzian conformal bootstrap, that's how they derive these bounds on the scaling dimensions of the radializing model. You might hope that you could do a similar kind of conformal bootstrap for these Euclidean conformal sum rules. So yeah, I guess we have tried that. You can actually find a bound on like the OPE coefficients in the Grady Lorentz Grady Ising model. It's like pretty far from being saturated though. So you could use these sum rules to find bounds analogous to this. For the CFTs.
But it's not like doesn't bring any new information for the CFT compared to the CFT bootstrap. That has already been carried out. Or it does.
Well, that's unclear. Yeah, that's like the hope that you might learn something more because of the Lorentzian. But then, like the different sum rules, the CFT should satisfy both of them. But we don't know how all these ones are for like constraining CFT data, I would say.
But for your CFT, well, you didn't really use the CFT, you just used an analogy, but all those CFT results, they should be interpreted in ADS for the eigenvalues of operators on ADS, right? So all the operator dimensions, they should all be interpreted as the eigenvalues of the spectrum.
Or holographic CFT.
Yeah. Yeah.
But this is like more general than that, I would say.
Yeah, it's more general, but that means that you could actually do the same thing you could do the same analysis on ADS, the whole thing.
Yeah, yeah. People did that, like in principle, this should be like somehow the same as what you've just said. I don't know in detail how it actually works though. Yeah, it's a, but yeah,
It should
you're right. It seems like this should be kind of the same thing. Like for a holographic CFT, there's an ADS theory with the masters given by eigenvalues, and there should be some calculation which constrains them and gives me some rules. But I don't know how to like get the CFT sum rules from a calculation like that.
No, you would do everything in ADS, right? Because you have the equations of motion in ADS. I mean, it's just, they're just Stone-Liouville equations for non-factorizable metrics, just Stone-Liouville problem. You could repeat the same analysis.
I mean, okay, yeah, I think you're saying, and then I can interpret like the bounds as bounds on the like scaling dimensions of a holographic CFT. Yeah, that's yeah. I agree.
Follow-up questions, then the speaker again.
So since they spectrum only depends on also mentioned shape. Yeah, but he said